So in this practice, we'd like to calculate mutual inductance. To consider the mutual inductance, we consider two coils. So like a coil 1, this is coil 1, and also coil 2. If the current is flowing the one of the coil, I sub 1, then this current induces the magnetic field. Magnetic field. This is the form of the magnetic field. So magnetic flux through the each turn of the coil 2, this coil 2, is proportional to the current in the coil 1, this I sub. Proportional constant we call the mutual inductance. So this means the number of the coils, this is n sub 2 turns, this is n sub 1 turns. Then coil 2 number of n sub 2 turns times the magnetic flux is proportional to the I sub 1. I sub 1 is coming from the current flowing the coil 1. And the proportional constant is expressed n sub 2 ones. So this is definitions of the mutual inductance. Okay, opposite case is also possible. So sometimes this is the coil 1. The coil 2. Sometimes the current is flowing the coil 2, I sub 2. Then this current generates the magnetic field. Magnetic field. Then actually magnetic flux through the coil 1 is n sub 1 times phi sub b1 is proportional to the I sub 2. This is the I sub 2 is a current flowing the coil 2. And the proportional constant m sub 1 2. This is mutual inductance. And we'd like to show you that this actually the m sub 1 2 is equal to m sub 2 ones. And the mutual inductance, this is m. And we'd like to prove that these formulas using this simple case. So I sub 1 is flowing, current is flowing to the small coils, but it's longer length of the capital L. Then the magnetic fields produced in the longer coils, this B magnetic field B sub 1 is expressed mu sub 0, and the number of turns per unit length you can find n sub 1 over L. This is number of turn per unit length times I sub 1. This is magnetic fields produced by the coil ones. Then we'd like to find out the magnetic flux through the one of the coils. This coil, magnetic flux. Phi sub B2 is equal to B sub 1 times cross sections. Only these regions produce magnetic field. So outside of these regions is zero, magnetic field is zero. So you have to multiply the A to find the magnetic flux through the single coils. So this means this is mu sub 0 n sub 1 over L I sub 1 A. So by substitute, these expressions is here. Then using these equations, you have to remember these equations. So maybe I have space. I need a space. Phi sub B2 equal mu sub 0 n sub 1 over L I sub 1 A. So the number of turns in the coil 2 is the n sub 2 phi sub B2. You can find mu sub 0 n sub 1 n sub 2 over L A times I sub 1. So by looking at these equations, proportional constant of the I sub 1 is m sub 1 2. So this corresponds m sub 2 ones. Okay, we could discover the mutual inductance of the m sub 2 ones. The opposite case. Simply I'd like to write so in this case is now in the last case the current is flowing on the coil 1s. So this case is current is flowing coil 2s I sub 2s. The magnetic fields produced by the coil 2s B sub 2 is expressed mu sub 0 n sub 2 over L sub 2. This is the L sub 2 n sub 2 turns times I sub 1. This is the magnetic fields produced by the coil 2s. Then, so this is a magnetic field by the coil 2s. Then the flux, magnetic flux for the single areas. Phi sub B1 is a B sub 2 times A on the cross section. This is the cross section. Is A, area of the A. Then you need to multiply magnetic field times areas. You can find mu sub 0 n sub 2 over L sub 2 I sub. So in I sub 2 A. The magnetic field is generated only the inside of the coil 2s. So this means only the this regions magnetic field is produced, but outside it's not. So this means you have to multiply the number of turns of the coil once. So N sub 1 over L is a number of turns unit length times L sub 2. This because the L sub 2 is the length of the coil 2 times by B sub 1. This should be the equal to N sub mutual inductance 1 to I sub 2. So if you substitute these expressions is here, then it becomes N sub 1 over L, L sub 2, mu sub 0, N sub 2 over L sub 2, I sub 2 A equal. Then L sub 2 is cancelled out. So we have mu sub 0, N sub 1, N sub 2 over L A I sub 2 equal N sub 1 to I sub 2. So this means M sub 1 2 is equal to this one. So we have M sub 1 2 equal mu sub 0 N sub 1 N sub 2 over L times A. This is the mutual inductance. So we have two expressions. First one is here M sub 2 1. Okay, and then M sub 1 2. And actually these two expressions is exactly the same. I proved M sub 2 1 equal M sub 1 2. This is the expression of the mutual inductance. This is the answer to this practice.